Well, good afternoon. As Stefan said, I'm thrilled to be here to speak about the soils of Iowa, just really review our state a little bit, and then speak about it from a pedologist point of view, which is what I do in soils, is pedology. But right up front, I want to say I'm honored to speak with PFI. I've watched PFI develop over since 1985, and I could not remember when you all originated, but I've really been impressed. I've certainly been a member for quite a few years since coming back to Iowa 22 years ago. So I'm thrilled to be here, and so Stefan, thank you again for inviting me. And so right up front, I'll say I'm a flexible speaker. I teach a fair amount at Iowa State, and so I'm really used to people interrupting me, asking me questions. So if you have a really burning question, I'm happy to answer as we go, or you can ask it at the end. Certainly if we get the microphone up higher. Okay, yep, I can do that. Oops. So like I was saying here, one, I'm honored to be here with PFI, and then second, I am a flexible speaker, so if you do have questions as we're going, you certainly can ask them. Alternatively, you hold them, that's fine too. If we get so far off topic, I'll get us back on and we'll get back to our presentation. So with that, just like to remind us, our goal is to just think about, was to understand the formation, distribution, and productivity of Iowa soils. And so the way we're going to do it is we're going to start by just overviewing Iowa a little bit before we actually get to this map and talk about the soils across our state. Because I like to remind us of where we live. Certainly I like to think about it whenever I'm talking to different audiences. And from there we'll talk about soil formation. So how did the soils form here? And where are they distributed? And then a little bit about soils and plants, although the later speakers will do a much more thorough job of speaking about how plants grow than I will. And then summary. And so with that, even before I start, though, I always throw in a few possibly useful web pages, URLs. And so you may or may not be able to read them, but this first one says Web Soil Survey. Probably most of us are used to that web page, but that's the USDA, Natural Resource Conservation Service's soil map for the United States. And as we all realize, there are soil maps available to all of us throughout the United States. And it's really a powerful page, and if you just type in Web Soil Survey, it will come up. It's available anywhere in the world. It's really nice. The second one you may not be able to read as well. I should have made it bigger, but it just says California Soil Resource Lab. If you type in those as your search words, California Soil Research Lab, you'll get a University of California Davis web page where it will have apps that you can download, all sorts of things. But those apps will connect to Web Soil Survey, and one of them you can download to your smartphone. It doesn't matter whether you have an Android or if you have a Mac or an Apple phone. You can download it to that, and at 70 miles an hour, as someone else drives your vehicle down the interstate, it will tell you what soil you're driving across. You can look up the soil properties as you go. It's Web Soil Survey made fast. And I mention this because, normally I teach undergraduates, or graduate students for that matter, and they're really bored fast, so they're always on their smartphone anyway. So I'd like them to actually know how to use it for something useful from my point of view. So Web Soil Survey is really powerful, but almost all that information is available through the California Soil Resource Lab app, and it's great. And if you get used to that and you tie it to Google Earth and it'll tell you how to do that, you can then go anywhere in the world and look up a bunch of soils information for that place. So those are just a couple things. After that, again, these are fairly small. I have the Iowa Geographic Server. So if you type in that, the Iowa Geographic Server, put that into your search words, what will happen is you'll get brought to a web page that has a whole bunch of different set of air photos and other information. But for example, I can look at this spot where Iowa State, where Sheeman Building is on the ISU campus, and I can look at the air photo from this year, seeing what the land looks like here and everything. I can take that back to all the way to 1939. I can look up air photos, and that's for everywhere in Iowa. So if you want to know about the land use history of your place, wherever it is, that works really nice. You can start looking back older and older photos, and it gives some other information like LiDAR or topographic maps and such too. Also tell you what watershed you're in. It's really a fun page. And then I have a few other, ISPAID, which would be some stuff Iowa State does on a soil database. The soils grid, that's a worldwide thing. European soil maps, that's worldwide. So a few other things in case you're interested. And all this, I think everyone has access to the PowerPoint, so you certainly can look on that, and then you get the live links. But like I say, I mentioned that just so as you get bored with what I'm saying, you can start looking up other things as we go. In terms of Iowa, How to think about Iowa. We all think of Iowa as just where we're from. And we all have it in our mind. Certainly as I travel around the world, I think about Iowa very much in terms of it's part of the North American Central Lowlands. We're very much right in this valley. And by the way, this map is showing intensity of cropping, really farmland, but arable land, intensity of cropping here in North America. And the darker the brown is, the more intense it is. So we're in the North American Central Lowlands, perfect place for cropping, as you can tell. We're also, many people would say we're part of the Central Plains, Mississippi River watershed. Alternatively, we could easily say, if you're more ecologically bent, we're part of the Prairie Province of North America. And so now getting more specific in soils, if we're in Eastern Europe, we'd be called Chernozems. And they were many of the first people to study soils, and they studied Chernozems, these black soils we're used to, many of us are used to very commonly. Or in China, they're called black soils, and both places have soils very similar to ours. Or here in the United States, we'll call these mollisols, and I'll come back to that. But there's any number of places, but basically we're right in this middle big valley that's broad and flat. We think in terms of our fields about the rolling landscapes and such, but on a broader scale, we're really in this nice central valley of North America. A few other facts, talking a little more about Iowa, and I always like to remind people, we're 56,000 square miles, right at that. We're 36 million acres. Our population is 3.1 million people. And I'll just stop and ask you all a question. So if I went back 25 years ago, how many people would there have been in Iowa? 3.1, 3 million. 25 years from now, how many people are expected to be in Iowa? 3.1 million. We don't change people-wise. So we have about 50 people per square mile. And anymore, though, I always point out Iowa is an urban state. 2/3 of us live in urban areas. From a population point of view, we're like New York or California. We're an urban state. But just like New York and California, from a land use point of view, we're rural. And we'll get to that. But we're rural. And well, coming back to this 65% urban, 40% of us just live in 6 counties. And I always point out that the university graduates that I work with, the people I work with in agronomy, all the majors I work with, environmental science, agronomy, it doesn't matter, global resource systems, they're all going to live in metropolitan areas. They'll commute 100 miles anymore. Many of us work with, service providers who are driving forever. We're becoming more and more urban. And again, that's just because I like people to think about it. Not because I'm trying to make any statement here other than I try to think about Iowa in terms of Iowa the place and try to separate from any, just try to know the facts is what I'm trying to say. 26 of us adults have about college degrees, so about 1 in 4 adults past 25 anymore have college degrees, but that's certainly split. It's about 30% now of the people in the urban areas have college degrees and 15%. And this kind of worries me. We're seeing that split get bigger and bigger. More and more of us that are go to university, start doing all sorts of things. We end up living in urban areas, and we're seeing a real change in the demographics. But you all see that too. 12% poverty, urban or rural, it doesn't really matter. So that's a few sort of cultural facts, just to think about it before we get into soils. Now, in terms of land use, even though I said we're an urban state population-wise, in terms of land use, Iowa is 90% farmed. When I look things up every once in a while, to the best of my ability to find it, and it's hard to figure this out for sure, but Iowa is the most privately owned state in the country. We don't have public lands. We have a little park here or there, and likewise we have some communities, but we don't have a Chicago or any of these really huge metropolitan areas. We don't have a particular large number of rivers. We don't have that many roads and highways. We seem like we do, but really we don't. And so we're 90% farms. We're heavily privately owned, percentage-wise, more than any other state. And within the privately owned land, we're almost all owned by farms. And right now, we have about 90,000 farms in the state. When I started college, when I was born in 1959, there was like 180,000 farms. So we're certainly seeing farm numbers decrease, but again, I'm not telling anyone here anything you don't know. That's part of why I'm really thrilled, like with Practical Farmers of Iowa, is I think you're really helping a resurgence of new farms coming around. And I think that's healthy for all of us. Let's see, within Iowa's 36 million acres and 33 million acre farmland, we grow corn on about 14 million acres. I left this, I give this presentation or topics like this internationally some too, so I left this in ton per acres. But our average yield of corn these days is about 200 bushels per acre. Soybeans, about 10 million acres, and the average yield there is about 55, 60 bushels per acre the last few years. Then, of course, pasture, forages, and forests make up about another 10 million acres of Iowa. And our farmland value varies depending where we're at in Iowa and such, but it certainly has gone up. It peaked a few years ago, now is stabilizing to a degree. So as you know, really what Iowa is we're a state where we grow a heck of a lot of corn, grow a heck of a lot of soybeans, put out a lot of forages, and actually forestry is a $4 billion industry too. So we do lots of things. Rural land use is what we do. We're a rural state in land use. But really, we do all that sort of stuff so we can produce pigs. And the most recent data I saw is that in a given year, Iowa raises about 50 million pigs. So at any given moment, there's only about 20 million alive. Pigs in Iowa don't have a particularly long life expectancy, as many of us here realize. But we raise a heck of a lot of pigs. We have hundreds of millions of chicken and such. And I mention that because when I used to work in Louisiana on a faculty member before I came to Iowa State as a faculty member. I'm an Iowa native, but I left for a while and then came back. Anyway, when I worked as a faculty member in Louisiana, came back in '95 to Iowa State, there were only about 30 million pigs produced in Iowa in a year. So while I mentioned the number of people staying the same, the number of pigs skyrocketing, number of chickens skyrocketing. So we're certainly changing how intensely we use the land across the state. So again, we grow these corn and soybeans is really what I was trying to get into. The forages even, not so much just because we want to grow them, but really it's to produce livestock, or what this map shows, the green is intensity of corn production, maize production in Iowa or in the United States, and then what the little dots are is when there is an ethanol, if it's a red dot, so an ethanol plant, a red dot, or the blue dot would be a biodiesel plant, a soy diesel plant. So that's a little bit about Iowa. And I run through that because the reason we're 90% farmed, the reason we're not a lot of public lands, I'll argue is because we have incredible natural soils. We also have weather that works really well. And the soils and weather we have really fits well with how our management has been, how we crop, how we like to crop over the last century and a half. So the reason we're this way is, again, that we start with this really incredible natural resource base. And by the way, what this map here is showing is the brown is row crop, the yellow is grasslands, pasture and such, and then the green would be where there's a larger proportion of trees. And then the little gray areas, which might be a metropolitan area, and we have a couple of lakes, so stuff like that too. So our key issues throughout the history of Iowa, and certainly remaining today, from my point of view as a soils guy, as a person really interested in working with people as they want to grow crops better, grow whatever better, is certainly drainage. Across the state of Iowa, we have about 1 million miles of tile lines, buried pipes. And really, for those of us that don't know what tile lines are, is they're typically, well, anymore, they're plastic, they're perforated plastic pipe that has a slight gradient that water can drain into and then drain out into a drainage ditch or such, and then ultimately into a river or wherever else it might go. So that's tile. And as a side, as someone that works internationally some, I always point out that when I first mention tile, outside of Iowa, maybe Illinois, the Midwest, when people hear of tile, me speaking about tile and soil, they're wondering why I'm talking about little stuff you put on a bathroom wall to talk about soils. For us, it's just part of life. We lower the water table. We have an incredibly shallow water tables is what it comes down to, and without it, we don't do it. But I think it said we have about 1 million miles of tile lines in Iowa anymore, probably a little more than that now. And if Emily Waring has anything to do with it, we'll have about 2 million in a few years. So really, Matt Helmers and such. So we have a huge amount of tile lines. And to say it differently, we drain our soils. We have about 20 linear miles of pipe in every square mile of Iowa. We drain. We have more plumbing outside. We have better plumbing out in our fields across the state than we do in our houses. We take it very seriously. So that's been a long-term issue, certainly across the state, and we still deal with it. Fertilization, we fertilize the same as anywhere else in the world. We have great soils, but that doesn't mean we can fertilize less because of it. We fertilize the same as anyone else who wants to grow things like we do. And certainly the history of Iowa is we have high erosion rates. For the last 70 years, we've basically led the country in corn production, total corn produced in a state. Over that same time period from a cropland, we've led the state or the country in terms of total erosion. but we'll come back to that. So that's a little bit of background. So now I should talk about what Stefan actually asked me to come and speak about, and that's the soils of Iowa, what the natural soils of Iowa are. So, excuse me. So the first thing I'll say, and this is what I really do most of my research and such on, is I think about what soils and how should we identify them, how should we classify them. Iowa has 507 soil series currently. And so what's a soil series? Well, around here we might say it's a Clarion soil, or if I go into southwest Iowa, it might be Marshall soil, or more northeast Iowa, I might have the Fayette, or I might have the Kenyon soil. So a series is just the name of the soil that we use for the local name, and we map 507 soils across Iowa. The differences between these 507 soils is based upon soil forming factors. That would be the parent material. So what the geology of one place or another is makes a difference in how we identify the soil and what we call it, and ultimately how we can use it to a degree. How long that soil has been forming, it makes a difference. What the climate is for that soil, and then also what the biota is. You know, is it forest, prairie, naturally biota, and then where it's at on landscape. So these are called Jenny's, for Hans Jenny, a Swiss-American scientist, Hans Jenny soil forming factors. But we have 507 soils is just a nice way to think about it. And the first thing we always think about in my world to understand soils and think about soils is parent material. And as an aside, that idea of parent material will really explain why we have so many tile lines we need. It'll also explain why we fertilize, like I say, we have high rates of fertilization across Iowa still on average, and everyone does it differently, but we have high rates, but why we fertilize a little differently than other places do who want to grow the same things. So, so we're going to start by thinking about what the parent material is and how that affects what's going on. And this is a nice map that sort of looks like a soil map, but actually what this is a parent material map of the state. Just saying, what are the major parent material regions? There are about 10 of them. And the first parent material I'm going to talk about would be right here in north central Iowa would be the best example. And right now we're in Ames. I have to stand a little better angle. So we're in Ames. We're right about here right now. Or over on this one, we're in Ames, so we're right about here right now. Sorry, I was trying to put us in western Boone County. We're in western Story County. So, and this is called the Des Moines lobe in my world, in our world. And for it, and really the whole state of Iowa, if we want to think about why our soils are the way they are, what's going on with the soils of Iowa, we need to think about glaciers. And the first thing I'll say about glaciers, they're huge. They're really big, and they shape our world. And for a few people who've had classes with me, they know in my classes I'll say they shaped our world, and we're still dealing with what went on with the glaciers. And the first thing I'll say about glaciers, you know, people often think about glaciers, they might have seen a glacier on some sort of cruise or something up to Alaska, and basically they start thinking it's a big chunk of ice. Well, it is a big chunk of ice, but it's more than that. It's a big chunk of ice that's flowing. And really with it on the north end for us, so up, say, in the Arctic area, where there's more snow than melting, we call that a zone of accumulation. Because in the accumulation zone where there's more snow than melting, is over time that snow just keeps getting thicker, it starts pressing down on it, and it starts compressing into ice. And as it further compresses into ice, it starts flowing. So it's really like a river in that we have H2O, in this case solid H2O, flowing downstream. But as it starts to flow with all that pressure, all the freezing to a degree on the bottom, all these things going on, that means any rock underneath it, any material underneath it starts eroding. So this stuff gets plucked up. It's a current that's moving, so that gets plucked up, gets picked up, and then it starts being ground up even as it's being carried. And then eventually it moves far enough that it melts. It gets warm enough wherever it moves to that it melts more than the additions come with the glacier. And as it starts melting more than everything else, we get an ablation zone. That means all the ice melts. And that means whatever it picked up to erode, the rock, the ground up rock now, the ground up minerals are deposited somewhere. So we're just talking about glaciers moving things around. Right. Picks it up, incorporates it, carries it. Just like erosion with a stream, you know, when you think about it, streams are really fun in that simultaneously a stream, at a given point on a stream, can be eroding something, it can be depositing something else, and it can be transporting something else. So that's why I say we think about them as rivers. They're really dynamic, they're really active, they're carrying things. then coming back, not only are they really dynamic, but did I mention they were huge? So this is the Laurentide ice sheet. And over the last 2 million years, by the way, there's been about 16 major glaciers. So this was one. This one was the maximum advance, the dark line, at about 2 million years ago. So, well, not that long ago. Yeah, 200 million. We'll leave it at 2 million for when it was advanced to here. But this was the overall advance. And so this would be about where Manhattan, Kansas is, Kansas City is, St. Louis is, Cincinnati. Runs out to where New York City is. But when I say huge, that means our glacier that covered here in Iowa, our different glacier that came here in Iowa, started way up here, a couple thousand miles to the north.
The first of the four?
All of them started up there and they worked their way down here. The Laurentide would include all four. This is really showing the maximum one. And actually the four, that just shows you learned about glaciers when I was in college too. We'd now say they were 16. So back when I was in college, it was so much easier to learn about glaciers as an aside. I learned there was a Nebraskan, a Kansan, an Illinoisan, and a Wisconsin glacier. It was really, really easy. And it was 600,000 years. And then people keep studying it, and now they realize there's 16 of them, and it went back 2 million years. Oh, excellent, excellent, thank you. So I was asked about the various glaciers, all of them, did they all run here? And yeah, for us, the various glaciers all started up here, worked their way down through here, and came down to where we are now. So we've had a bunch of glaciers covering our part of the world. By the way, Northern Europe, which has many of the same features we do from a soils and land point of view, it looks like to me much of those areas had the same glaciation impact. Big feature around the world. And it might affect, when we have comparable soils from one place or another, it's getting into this parent material. The geology is similar, so we're starting with a similar starting point, and that would expect that under similar weather and such, we're going to see similar soils end up that you and I are managing. So by the way, that leads me into, though, here in Iowa, we often talk about the Des Moines lobe. That's the green part on the one map, that central lobe. Well, to you and I, by the way, we think of this as huge. It's 10,000 square miles. That's a big area. It includes northern half of Des Moines, certainly Ames, going up to where Lake Okoboji is, going up Clear Lake almost to Mason City. You know, it's 10,000 square miles. But I want to point out, compared to that glacier, that the Des Moines lobe, which I think I calculated has about, I don't know, $70 million worth of farmland on it. That Des Moines lobe is that little dribble of ice cream that's on your hand as it's melting. In the world of glaciers, it doesn't even count. It's so tiny. But for us, it's kind of big. So from a human point of view, it's big, and it's really important. It covers about 10,000 square miles. That means about 100 feet thick on average. It's 800 billion tons of new sediment came into Iowa. That 800 billion tons of stuff is going to weather into our soils as we get into it. And if you want soils, it's nice if you refresh them every once in a while with new stuff. So again, it's huge from a human point of view, but in the world of glaciers outside of Iowa, no one cares about it. It's too small. Just isn't in our world. And in case you think this is completely needless, and maybe it is, I want to point out that if we look at the north central United States, where we often think of like the Corn Belt or this major cropping component, I want to point out all the glaciers covered right here. And would you agree that really fits the Corn Belt nicely? So I'd start saying that maybe there's a reason we do things the way we do here, and it has to do with we start with the right, or a parent material we humans know how to work with, both here in North America, certainly in Europe, in Asia as well. By the way, the other thing I want to point out is I've talked about how big these glaciers are, and here it is, and now I'm just focusing on this part of the world, and I just have a question for us all here. Why do all the glaciers stop right here in north central United States? Why do they keep coming down here and they keep stopping? There's been 16 of them over 2.5 million years, and they all come to the same place and they stop. And did I mention, by the way, that if you're on the north end of it, that means whatever stuff you have that might form into a nice soil gets picked up, taken by a glacier, so only the most resistant rock gets left behind. It all gets ground up, dumped for us in a nice ground up way. If you're a root, do you want to grow in pure rock or do you want to grow in rock that's been ground first? So we're in the end that gets all the good stuff. The Canadians, they get the stuff where you have lakes that you can go fishing in. You know? So we came out okay on this deal. So my question is, why do they all stop here? Because my PhD, by the way, is from Ohio State, so I did a bunch of research out here too for my PhD, and then I'm from a little town of Renwick, Iowa, so right up here. And so I've done a bunch of work for my master's as well here in Iowa, and then since I've been here for almost 23 years now as a faculty member, I certainly work across the state. But you know, it doesn't matter. As I work here, all these glaciers they all stopped here. Why is that? Okay, so global warming, yeah. I like warming. Well, where are we? Where's Ames in the world? And people start telling me the Midwest, and I always point out to my other students, when you travel internationally, never say the Midwest. They assume you mean you're living in the western part of the United States, because it's west, and then middle, north, south. Well, actually, we're in the eastern half of the United States. It's a lot closer to New York City here than San Francisco. So I always say, just talk about you're in the central North American lowlands or something like that. But yeah, global warming. Would you agree if we go up to the Twin Cities, Minneapolis, St. Paul, we'd be at 45 degrees north latitude, so we're halfway from the North Pole, halfway from the equator. Here in Ames, we're at 42 degrees north latitude. Does that mean even when there was a glacier here, every winter it's cold, like it was a couple days ago here, but every summer it's hot? So if you're a glacier, we're now close enough to the equator, there's too much melting. You can't go any further down. The amount of new ice being added, sent down our way, and again, it's a river moving down, can't get any further. It all has to melt. So glaciers are a major feature for our parent material. We see lots and lots of glaciation happen. The one exception in this part of the world for glaciation is, in this part of the world, called the Paleozoic Plateau. For those of us from far northeastern Iowa, such as those who've been there, Decorah, I was going to say, I almost said Luther College, but Decorah, so Alameda County, Winneshiek County, those areas, there's been very, very little, if any, glaciation ever here. But the rest of the area you can see has been heavily glaciated. And they all stopped here because they had to melt. So the next thing that makes me think, okay, well, what else is going on? Because we want to understand the geology of Iowa, because that's our parent material. That's our starting point for actual soils you and I manage now today. And so the next thing I need to mention is what goes on off glaciers. Well, I said they all stopped here because the summers are too hot. They melt. And realize, first of all, that when I say glaciers are huge, realize there was so much glaciers in the world, even 15,000 years ago, or a million years ago, depending which glacial advance I want to talk about. But there was so much ice in those glaciers tying up so much water, and the amount of water on Earth doesn't change. It's constant. So when you tie up that much water, it lowered sea level about 100 meters. That's 300 feet lower. That's really a blast. 300 feet lower sea level. What that means then is we could have walked from Miami to Cuba. Or alternatively, people could walk from Siberia into Alaska. Sea level was so much lower. But the reason I mention that is you have so much ice tied up there, and I'm saying every summer this front of this glacier is melting. Can you imagine how much water is melting all that? The way to think about it is think about Squaw Creek. There's a little tiny stream just a half-mile east of Sheeman here. Today it has about 20 cubic feet per second of water, so 100 gallons of water flowing down it. Well, that means on average it's about 10 inches deep, and it's 50 feet wide, and it's flowing maybe a foot per second. Just a little stream. Not much. Back at the time when this glacier was melting on a hot July day, it would have been the size of the Mississippi River. And it's melting from an ice mass that's carrying, did I say, hundreds of billions of tons of sediment that's ground up in it? So all that sediment is also rushing out the front. So that starts getting to what's going on off glaciers. We have huge amounts of outwash. Or to say a little bit differently, so here is what I'm saying is every summer, every stream, every river in the world around here had more water than you can imagine, and it was white water. If you were a kayaker, you were going to be in it with boulders the size of that table, 4 feet tall, 4 feet wide, diameter boulders, and they would be bouncing along with you, so you wouldn't last very long as a kayaker. It'd be white water. It'd be kind of exciting for about 8 seconds, but then it would get old. But that's every summer, all that water and sediment. Every winter, that glacier front refreezes. It's cold as can be. So now you have all this sediment that was being carried down, all the water goes away, that sediment gets dropped in the valley. And associated with a glacier, you have incredible winds around the front of it, whipping. And those winds start eroding all that sediment, and you start getting loess. Wind deposits sediments. So for those of us not from north central Iowa, but we say we might be from the Loess Hills or western Iowa, or we might be from up at Decorah, where on the tops of the hills we know we have beautiful loess-derived soils, the Fayette soil, for example, or across eastern Iowa, we have loess. And so on this map, and these numbers are in feet, we see that in western Iowa, over by Missouri Valley or such, it says 64 feet. Actually, it's over 100 feet. It's just this map can't show it very well. By the way, if you just go a few miles away, it's 32 feet thick, 16 feet, 8 feet, and then by the time you get, say, Edina, Missouri, northeast Missouri, Kirksville, Missouri, it's 4 feet. That's because this is all sediment blown out of the Mississippi, or excuse me, Missouri River. So there's lots and lots of sediment being blown across here. Likewise, some of the winds whipped up this way because there was another glacier right here in South Dakota at the same time as our Des Moines lobe. It blew winds this way. We see 30 feet of loess or so in Sioux County, and then it gets thinner and thinner as we go up to Sibley County and such, or Osceola County, Sibley town. Or we can have some of these things in northeast Iowa and such. So the loess, this beautiful silt that you and I often think about in Iowa and incredibly productive, came from the glaciers too, but indirectly. Yes?
How deep would the Mississippi River have been during the summer outwash?
Yeah, so that's a great question. So how deep would it be? Conservatively around here in the middle, it'd be carrying 20 times as much water as it is now. So it would have been both wider and deeper and a lot faster, because the gradient would have been a lot steeper, because right now if we go down to where Burlington is or so, the actual Mississippi River level is just certainly less than 500 feet above sea level, but we might say 500 feet above sea level. It has 500 feet to drop as it goes down to where New Orleans is, well, past New Orleans, to the Gulf of Mexico. But back then it was another 300 feet down. So that's a bigger gradient, and that means the water's flowing faster. So it was another world back then. And the most recent glacier was 14,000 years ago, which, by the way, is when humans in Mesopotamia started doing agriculture too. And many people will argue, and certainly lean toward that glaciation and the change it was causing climate worldwide was having people who were smart then, just like they are now, start thinking about changing it differently. But a lot more water. Excellent. A lot more sediment being carried too. So, but coming back to in Iowa now, when we look at this across the state, we have 600 billion tons of loess, which is silt and clay, so the fine-grained stuff that blew across Iowa and made incredible soils. And for those of us that work with loess soils, they're really nice. But that's 600 billion tons, 600 billion tons of little tiny stuff that got blown across our state. The big stuff got left in the valleys. So when I say they're huge and they're moving, they're carrying lots and lots of stuff. By the way, I asked down here, why is loess thickest in western Iowa? And it's about 64 feet right here. And if you go into Nebraska, the thickest loess they have is about 32 feet. So the thickest loess in Iowa is twice as thick as the thickest loess in Nebraska. I'll ask people, why would that be? The thickest loess is in western Iowa, the Loess Hills, as we know, and then we can see it other places. But why do you suppose just across from one side of the river to the other in Missouri River, it's so much thicker on our side, Iowa side, than on Nebraska side? Prevailing winds. 2/3 of the winds blew east, 1/3 of the winds blew west. That's where it took it. And so from this, and in my world of predicting soils and mapping soils, knowing these things, by the way, becomes really useful, because I can start understanding exactly where I'll find what soil property, because wind's a great sorter. So by the way, the other thing I always like to mention, in Iowa, we're rightly proud of our loess, and we have incredible loess. But I want to point out, to get loess, you just need exposed sediment and wind. And so we have a tremendous amount of loess throughout the North American lowlands, as you can see. And some of it's only 40 inches thick or so. This map would be anything over about 40 inches thick of loess. But we have a lot. We certainly have a lot in Europe where it wasn't glaciated. So looking at Ukraine, Russia, throughout Europe, certainly in France as well, Germany and such. Certainly if I go down to Argentina, Uruguay, see a lot of loess. And I go into China. And I mentioned that one is it's nice to know. Oh, by the way, there was a huge amount of loess. When I was down in Louisiana, at Lafayette, Louisiana, I went to Baton Rouge, I dealt with the exact same loess we deal with here. Because outwash from the river went all the way down there. The pulses in the river changed all the way down to the Gulf. And so that means every winter there was a bunch of exposed sediment, even way down there, blew up Loess Hills. So you go to Vicksburg, Memphis, something like that, you see the exact same loess we have. But the thing I really want to point out with this slide now as we look at, so before I suggested the idea that we have a lot of cropping where there was glaciation. I tied it to the Corn Belt. Would you also agree, worldwide, we have a heck of a lot of cropping wherever there's loess. We see the big farms everywhere in the world tied back to this. So from a soils point of view, it really helps if we start thinking about what are we starting with. And then there's a few other things like alluvium, if you get the right type of sediment deposited by rivers and such. There's really only 3 or 4 geologies that really become really important from a parent material worldwide for our big cropped areas. Yeah, it's considered quaternary, same age period as what our Loess is, and it was tied to alpine glaciers here in the Andes, and then sediment blowing. So then alpine glaciers depositing sediment, and then with the intense climate swings from summer to spring, blowing the same sort of sediment around. In the case of northern China and such, it was the intense weather of the Gobi, so of the desert up here and such. But again, the same thing, winter drying and such. Fun question. Excellent. Thank you. Yes? Yeah, incredible. Well, there is loess there, but it tends to be thin. And then it's a bunch of other, probably, my best guess is it's sort of an erosion surface coming off the mountains as well, where there's been great sorting and such. And, repeat the question. So it's about the Punjab area of India. It's incredible cropping. And some of that's alluvium, so water deposited. Some of it's wind deposited. There is loess there. And then as well, there is some petasediment, as I call it, or erosion surface, coming off that's sorted and help make things finer. Phenomenal question. Sir?
Why was the world so windy, and how much windier was it?
Well, in a sense, the way I'd say it, and I'm not a meteorologist, so I'm not qualified to say how much windier it was. But anytime we have, from a physics point of view, if you have intense changes in temperature in a very short distance, we can get winds. And so if there's a glacier sitting there that really represents Arctic conditions way up north, but it slid all the way down to where we are, but then we have these tropical warmth coming up here in the summer, we have those really intense temperature differences, moisture content differences, evaporation. That starts putting a huge amount of energy in the air. I think it's something like for every raindrop that falls, as that water condenses, there's 600 calories of energies re-released to the atmosphere. That's what we often see in a thunderstorm, incredible winds as well, because to have water as vapor, you have a lot of energy stored in that vapor, and when it condenses, all that energy gets released. And so we have these big temperature differentials, water vapor differentials that result in a huge amount of energy being back in the atmosphere, moving the winds around. Fun question, sir.
Definition of loess.
Great question, yeah, and I use this all the time. I should talk about it. So the definition of loess is wind-deposited silts and clays. And so that means I need to say a couple other things. So in our world of soils, we generally talk about soil texture. So I'm on an aside for a minute. But with texture, texture just refers to the amount of sand, the amount of silt, and the amount of clay in the soil. Sand would be any particle between 2 millimeters to 0.05 millimeters in diameter. What is sand? Sand is exactly what you're used to at a beach or when you're building with it and stuff like that. Sand is the particles we're used to seeing and rubbing in our hands, and they're sort of gritty when we run them through our fingers. Silt is a particle between 0.05 to 0.002 millimeters in diameter. So silt is smaller than kitchen flour, but it feels like the flour we might bake bread with. It's actually smaller grain than that, but it's like that. By the way, and then clay would be any particle smaller than 0.002 millimeters in diameter. We need a microscope to see the clay. And in case you're wondering why people like me break things out by those sizes, sand grains are really good at having water infiltrate, really good at draining water. And actually the sand grains, by being a little bit sharp when we rub them between our fingers, when you put a load on them, you stand on them, they lock together. Likewise, if you put a little water between sand grains, like on a beach, they lock together. And so we've all experienced that at one time or another, or we've seen it in advertisements certainly, where if you're up on the dry part of a beach, you actually sink some, and then it gets firm. And that's the sand grains are shifting, and then they lock. But we get to where it's slightly wet in the beach, it's packed so tight, or so to speak, feels packed, and that's water pressure pushing the sand grains apart, and they're locking. And we'll see cars drive 100 miles an hour down a beach on that. So what sand, though, is really this larger particle, gets into water infiltrating air, oxygen moving in the soil, CO2 moving out. So sand grains give us some strength. The silt grains, the reason people like me care about it, is that slightly smaller particle. What that is now it makes the soil a sponge. So Loess is predominantly silt in almost all cases. So 60% silt, 70% silt. And by having silt, that size of particle being the dominant size, that means whatever water comes into it is held as if it's a sponge. That means a plant can pull it out. With the sand, alternatively, the water all drains through. The clay particles, by the way, are shaped like your sheets of paper. And I didn't bring any sheets of paper today. But clay particles are so small and they're shaped like sheets of paper that actually they pack really tightly together, number one. And then they're a little bit charged, which we can talk about later. They have a slight charge, they pack close together. And that's why they're so small and shaped like sheets of paper that if any water gets in between them, that water gets sucked to both clay particles. That water can't come out. We've all seen plants in drought with clay. But not only are they that way, but if they get moist, then the clay particles are such they slide across each other. And so we've all seen it when we step on it in a wet clay, we get sink down and we get stuck. And then since it's so much surface area and a slight charge to it, it just sticks to your boot when you try to pull it out. So these three sizes of sand, silt, clay behave very differently. But coming back to what is loess? Loess is wind-deposited silt and clays. And so the sand hills of Nebraska, by the way, are also wind-deposited material, but they're sand. We have wind-deposited silt. Which one's a lot better for plant root? Silt.
So then topsoil is predominantly silt?
Some are. So if you're lucky, your topsoil is often a silt loam, or it's predominantly silt with some sand and clay. The right balance is ideal. But and in Iowa, the most common, of the 507 soils we have, the most common A horizon. So I was asked, topsoil is predominantly silt. It just varies. The predominant texture, sand, silt, clay ratio of Iowa soils tend to either be silt loams, so a lot of silt with a little bit of sand, a little bit of clay, the right balance of those things, or loam, which would be an equal balance of all three, sand, silt, and clay. And by the way, as an agronomist, if I want to grow really good crops, I always tell people if you can, start with either a silt loam or a loam. We're really lucky. If we had the sand hills in Nebraska across all of Iowa, Iowa State wouldn't be here. We could afford one public university then, it would be over in Iowa City. They predate us. You know, that's just the way it goes. Great questions. So anywhere we see these losses, and we're based on tying these conversations together, anytime where we see these losses, immediately what I think about is a really silty environment. And that means I really start thinking about great water holding capacity that's plant available, and that means I think less drought issues in the summer. So that's how I see these things like this. Great questions. Other questions or anything? Coming back to it, this is where the Loess is across the world, the major Loess units. There are smaller units everywhere, but just like everything else. Excellent. So coming back to it, our soil map now, finally speaking about soils of Iowa. So the first thing to realize when we look at this map, these different colored zones, we put this map out, people like me put this map out, because it's really saying where the different parent material regions are. This is called the Des Moines lobe. It's an area, the greenish yellow right here in the middle, that was deposited most recently by the most recent glacier. It left here, the glacier reached Des Moines 14,000 years ago. By 12,000 years ago, it had melted out of Iowa. So it was up in Minnesota, and it's still melting north, up in Alaska now, up in northern Canada. These areas here, this area here is the Missouri River floodplain. So in far western Iowa, there's the Missouri River floodplain, all that outwash sediment deposited by the most recent glacier, and from it we get the loess that blew all across Iowa. So these are just different thicknesses of loess. These different zones are different thicknesses, getting thinner and thinner. The other thing is wind blew it further and further, the amount of silt, the water holding stuff, content decreased, and the content of clay proportional to silt increased, and so these are also getting thinner loesses and clayier loesses. So we're seeing these different zones across Iowa. This was a different loess zone, really associated with like the Des Moines River and such. The green area here, this KFC, the Kenyon-Floyd-Clyde soils, that's a parent material zone as well. It's called an Iowan surface. It's actually an erosion surface, like I was mentioning with the Punjab region of India. It's actually a natural erosion surface that goes back about 20,000 years. When the glaciers were leaving Iowa, the climate changed so intensely that the whole area started eroding. But it was natural erosion. And so we're getting these different parent material regions. So what I'm trying to point out is the first thing I look at this map, coming back to the soils of Iowa, is I start thinking about geology. And in Iowa's case, as you can tell, I think very much about the geology from a point of view of glaciers, and then wind, so to speak, off glaciers, blowing sediment around. And from that, I can really start explaining our state and different regions. But as I said earlier, to really understand the different soils of Iowa, we shouldn't think just in terms of parent material. That'd be sort of like thinking, you and me just thinking about our parents and their genetics. Rather, we're all also products of the environment we grew up in, we interact with now. And so from the environment point of view, climate and biota also matter. And those things come into this map as well. And the way I would say that is just remind us that while the mean annual precipitation of Iowa these days is more or less 33 inches, so we crawl across the state, we have about 33 inches of precipitation on average, and the mean annual temperature for Iowa is about 50 degrees Fahrenheit, so about 10 degrees Celsius, so on, the average is that. But at the same time, if we're from Lee County, the best sounding county in Iowa, don't you think? Isn't that a beautiful name, Lee? But anyway, the rainfall there is about 40 inches on average a year, right? If we go up to Lyon County, another beautiful county all the way up northwest Iowa, very nice area, rainfall anymore is maybe 28 inches a year. So we have this gradient of rainfall across the state that's big, 40 inches to 28 inches. We have a gradient of temperature, much warmer down here, much colder up here on average. Any given day it can be anything. And then we actually have water demand varies across the state, so your plants, their water stress all changes and such. So that climate differences today, but certainly naturally as well, so if we go back before you and I were trying to farm Iowa, that climate difference also resulted in big changes across Iowa. Eastern Iowa, these green things, these would be areas where forest dominated. The brown area here, this would be areas where prairie dominated. And then there'd be wetlands and such too. And then savanna, what savanna is a combination of forest and prairie. And it's actually more complicated. These forest and prairie have been fighting each other across Iowa for the last 2 million years. One moves in, one moves out, depending on how global climate changes going on associated with glaciers and such. So what we have is these different zones. And as an aside, as I mentioned that, I'd like to point out that across Iowa, you can see actually coming up the river valleys was forest. And that's because for the last 3,000 years, Iowa's had enough rainfall for the whole state, basically, especially the eastern 2/3 of Iowa, to support forest. And those forests keeps trying to migrate and replace the prairie, ecologically speaking, but then the Native Americans certainly burned intentionally. There was lightning strikes, would burn the trees back. And so, so these alpha sols, these forest areas, would actually cover more of Iowa naturally than they do, and that gets into that the prairie has been maintained there. But the bottom line is we have prairie areas, forest areas, savanna, wetlands, all sorts of things. But at the statewide level, we'll just think really in terms of prairie and forest. Locally, we can think about all of these and a few more things within them. But we have the different regions of Iowa. So from a climate and biota point of view, what I'm really saying is to think about Iowa. Most of this area out here, these big areas, are prairie-derived. The eastern Iowa, the river valleys and such, we see are very much more forest-derived. And that comes back to southeast Iowa. Eastern Iowa gets much more rainfall, 950 millimeters, 38 inches or so. Western Iowa, way up here, might get like 28 inches, 650 millimeters or so. And so east was forest, west was prairie. We get different soils. And so some of these soil associations, like the Fayette, Dubuque and such, those would be very much forest, Dinsdale and such, savanna, some of the middle of it, and then mollisols or prairie in the western Iowa. So we get these differences. And I'm going to start using a couple terms. One of them I used early on. Whenever I say the word mollisol, I'm really saying a soil that's a black soil. And it's more or less means it's a prairie-derived soil. And we have these very thick A horizons that are really black. In this case, it's white here because there's calcium carbonate in it. It's not from leaching. Actually has a lot of ground-up limestone, if you will, in it. But this has to be more than 10 inches thick, have really good structure. So the soil really is nicely granular. Has to have greater than 6% soil organic carbon, so not of organic matter. And it has to have what's more than 50% base saturation throughout this depth, which just means it's naturally fertile. So we have a lot of mollisols wherever we dealt with, oops, let me come back one more. We have a lot of mollisols wherever we have these prairies there for a few thousand years. Beautiful soils, very incredibly productive soils. And so in Iowa's case, we have 98,000 square kilometers, so 2/3 of our state. So if you want it in acres, it would be about 20 million acres of Iowa is these thick, black A-horizon soils. They're different from eastern Iowa and western Iowa, and so that's part of what you and I deal with as we manage our fields. Depending where we're at in Iowa, they can actually have a really clay-limiting B-horizon, much more dense, and in some cases root-restrictive zone. In western Iowa, they tend to be more uniform with depth. And so that's what the difference between an RG Udall and a haplodol. More than you probably want to know right now. This endoaqual term, that just means the number more wet. And so when I mentioned before these million miles of tile lines in Iowa, bluntly, that million miles of tile line lowering water table, that's really designed when you have these endoaqual, aquic, wet soils, lower the water table so they'll produce like they're one of these. So we have a distribution across Iowa, and really all I'm saying is this map is a parent material map, but it's also a map of how the climate caused biota, the ecosystems, to vary across the state. And those ecosystems, as they weathered, plants growing in a soil starts changing the soil, and you accumulate organic matter, you build structure, you change all sorts of things beyond what I was going to cover in a little more than an hour. So coming back to the forested areas of Iowa, this area of Iowa, we're very much alpha soils. So we have different regions across the state, very different soil properties here, because an alpha sol on average looks something like this. So you notice you don't have that nice thick black A horizon many people are used to. It's a thin A horizon, and then this gray is not calcium carbonate, it's not ground up limestone. This will be an E horizon, so often very, very acidic. So it's a thin surface, thin epipedon means thin surface horizon, and then it'll have a clay-enriched B horizon. So really what I'm trying to say is across the state, because of these ecosystem differences, which are related to the climate differences, we start seeing very different on average properties as we go from one soil region to the next. So that's, yes, go ahead. Yes, there are a bunch of questions. I'm happy to do it. Yeah, I'll try to remember to repeat the question. Sorry about that, Stefan. Yes, please.
Okay, so those forested areas,
Yeah.
were they here in the 1880s?
Yeah, so this is really fun, is, I put this up, I'm talking fast. This is the map showing where the forests naturally were at the time of the public land survey. So in the 1830s. And so the public land surveyors, the people after the Louisiana Purchase who came across, walked across, surveyed, the edges of the square miles, every section, they would record what's there. And this was where there was dominance of forest, or at least savanna, with a heck of a lot of trees there. Go ahead. Let's answer the questions. I have something I want to say. Yes. So that's where the trees were. Yes. Sure. Yeah. Sure, excellent. So the epipedon would be the A horizon for the most part. It's the surface of the soil, so most people would call it the A horizon. The solum would be the depth that includes the A, if there's an E horizon, as well as the B horizon. So everything down to where the parent material hasn't been weathered. Great questions. So what are these terms? What does epipedon and solum mean? It means surface of soil, the A horizon, and then the whole profile down basically to rooting depth. I'm trying to get better at actually do what you say, Stefan. Was there another question? By the way, as an aside, yes, we'll come back. Okay, go ahead, sir, and we'll come back to you.
So would you expect to see then a greater definition of those lines in the forested soil than you do in the
Very much so. So to say that, come back to that a little bit differently. In this type of soil, they're really boring. As a pedologist, I really get tired of studying mollisols, because in many of them, for the meter and a half down, everything changes so gradually, and it's also nice from a root point of view, that I'm not dealing with anything that's exciting. It's interesting, it's important, but it's really boring. These things, so to say it a little bit differently, often in a black soil like this, often in Iowa, and this is a unique one from northwest Iowa, but often in Iowa for the top 40 or 50 inches, the natural pH might have been 6.5, 10 inches depth, 6.4, 20 inches depth, 6.7, 30 inches depth, 6.9, 40 inches depth, 6.9. In this alpha sol, I can show you examples in these alpha sols where the top, the A horizon, this very top, the natural pH might be 6.5. At this depth, the pH might be 4.5. At that depth, it might be 8.5. And from a root point of view, nutrient availability point of view, those pH swings like that would be like if this lecture was going on where for the first 15 minutes, we had the room set like this. For the next 15 minutes, all the cold air from yesterday blew across us. And then for the last 30 minutes, it was 90 degrees in here. It's intensely different if you're a root trying to live in those different environments. Ellis. This argillic. Okay, so in the actual soil. So great question. What's actually in the soil? That's where, coming back to the very third slide or so where I said web pages are kind of boring. If you're bored, you start looking at. To get that information, to really understand in your particular soil, in your field, I would go to Web Soil Survey, or I'd use the California Soil Survey app, and I would call up my particular soil, and I would then read the description, and I'd look at the data they have published on it, and I'd say, oh, this is what was depth. Because it'd be like saying, who is sitting behind you, sitting behind you? I can either talk about person to person, or I could try to give you average, but it's really specific. Every soil has its own characteristics. So I'm not answering your question very well, but that's where I need to look up on the information to get it. But so every soil is unique, sort of. Okay, so the base of the solum, or the epipeton, it means I no longer have significant organic matter addition. So it's the depth where I have not much organic matter addition anymore. Sort of. It depends where I go in the world what it really means. That's why I'm having a hard time. Here in Iowa, it's our organic matter addition. Thank you, Stefan. I thought I'd be done with all this by 20 minutes. I thought people would be bored. So it really means the depth of organic matter addition here in Iowa. If I go out west to Arizona, I'm going to have to do that a little differently because they don't deal with organic matter addition in the deserts very much. If I go down to Brazil, I deal with it a little differently, what it means. Great question. Yes?
So does soil, as in argillic, does it develop its fertility from the bottom up or the top down?
Great question. So how does a soil have its inherent fertility and such? Where does it start? Well, the number one thing is you want to get lucky. And that's a terrible thing to say, but coming back to the glaciers here that cover Iowa overrode a bunch of limestone beds north and west of here. That picked up a bunch of calcite, which is ground up a bunch of limestone, so lime, and they brought it very rich in calcium, magnesium. Likewise, they overrode a bunch of apatite, the mineral apatite, which is the phosphorus mineral we use to get fertilizer from. In Canada, they ground that up, they deposit that. So all that inherent fertility was in the soil profile to begin with. And then what happened is as weather started to, rain leaching through there, started to dissolve things, the phosphorus, that calcium, that magnesium, all became released. And now depending on whether you have plants growing, or grasses growing there, or if you have forest growing there, how it gets cycled back through the soil over time is different. So what I would say is it came initially from what minerals it overrode and got deposited, and then depending how the climate interacts with dissolving it, and then what type of plant you have starts controlling, or you see more of it down deep or more of it up high. Does that sort of explain? By the way, I want to mention it that way because I want to point out Connecticut, New York, those areas had exactly the same glaciers I've described here cover them. They overrode a bunch of acidic granite. So the minerals they got don't have any nutrients in them. So when they weather, you don't see the same plants growing there. You don't see the same crops. Starting with the right genetics, the right process, the right genetics helps. We're lucky. The last thing, and then I'll answer a couple more questions, that I want to say is, as an aside in this discussion, it's more than what we can really talk about today, but I want to point out, I mentioned that rainfall has been increasing in Iowa for the last 3,000 years. Natural rainfall, and it gets into climates, the glaciers moving back, so that natural rainfall increase for the last 3,000 years means, like I say, for the last 3,000 years, we've had enough rain in the eastern two-thirds of Iowa to have forest take over. Deciduous trees need a lot more water than prairie does. So you need wetter conditions, more rain. But for the last 3,000 years, we've had enough rain to produce deciduous forest, and yet we've had soils that formed under prairie over much of the state, if I'm a corn plant, a plant we really like growing in our state, big, big grass, do you suppose its roots really like a prairie-derived soil? Yep. Do you suppose they like the rainfall of a forest system? You bet. That's why we have corn here so much and not wheat. So all these things start coming together to explain why we can do what we do. So it explains soil distribution. But I saw another question. So you had another question, I think. Sure. Yeah. Right. 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 Yep. Yeah. Great. So the question is, okay, so we know in a soil like this, and really every soil, but especially a soil like this, these horizons that have formed from the parent material under different types of weather conditions and different vegetation, they have these different zones, these different horizons in my world, these different zones have very different properties, and sometimes really abrupt contrasting properties in terms of texture, bulk density, pH. So what depth should we sample? And the question also point out that laboratories will say sample typically the top 6 inches or whatever. That's because it's a correlation. So from the point of view of giving people the most information fast, since all the roots have to stop, and basically all the roots always start in the top 6 inches, you start with there, you give that information, and in general that will help explain about 70% probably what the plant will do that year, at least early on. But yeah, if you really want to manage successfully for the 21st century, I want to know about more things with depth. But it's sort of like going to the doctor's appointment. When in doubt, to take your pulse, blood pressure, and temperature. That will give you a nice starting bit of information for the physician. If they really want to work with your health really sophisticatedly, you need more information. And that, you're right, on these sort of soils, I want more information. I do some work in East Africa and such with soils, very different set of conditions. I need to know more about what's going on with depth, because the top 6 inches will maybe give me 70% predictive ability and probably often only 40 or 50%. But it's cheap and easy and it's consistent. Phenomenal observation question. Yes?
What's the origin of the clay in the extreme eastern Iowa hills that were literally glaciated?
Yeah, so I mentioned the idea of rainfall. And the thing, so the question is, what's the origin of the clays in some of our soils in eastern Iowa where it wasn't glaciated, or anywhere in the world that wasn't glaciated and such, or any soil. There's lots of ways you can get clays, but the easiest way to think about it, in case you had loess or even sand, is if you give me a few thousand years of rainfall, I start dissolving a sand grain, any grain. They start dissolving. If they dissolve, they're getting smaller. And as they keep dissolving, they're getting smaller and smaller, making smaller particles. But the other thing going on is everything that's dissolving is now floating around in solution. Some of it gets picked up by plants, but some of the silicon and aluminum doesn't. And this starts reforming into little tiny crystals, clay crystals. So the weathering process itself results in a lot of clay. Because these things get smaller or they reprecipitate. And what am I saying when I say reprecipitate? Some of us have known people who leave a glass in their bathroom for like 2 years. Maybe you know a college student or something like that that did that the whole time through college. Is that glass or plant pots, potted plants, do they all have a nice rind of new minerals that formed? In natural soils, we start seeing clays forming. So we see these weathered different ways. Great question. I don't know I answered it very well. I'm going to run through a couple more slides, but really coming back to our map, I really want to point out that whenever I think about Iowa, I think about some of these regions, and the first thing I want to know is, so if you ever call me with a soils question, I want to know where you're at. And I want to know where you're at because that's going to start telling me what soils, parent materials you likely started with. And from that, I have some idea what's likely to be going on. And then from that, I need to know where you're at because that also starts telling me what's been the climate and the ecosystem that caused your soil to naturally form. And then I'll cheat and look up Web Soil Survey and get even more information. And then I'll ask you about what you're managing with. So with that, the next thing I want to say though is the discussion we've had now has been big picture, one region of Iowa versus another region of Iowa. What I want to point out, relief or landscape is also matters, and what that's really saying is within our field, within our given site, we have different soils on top of the hill to the bottom of the hill. And I'm using this as, this is just what you might find around Ames. As you drove to Ames today, came to Ames, on Highway 30 or the interstate or whatever route you brought in, you know, one of the blacktops or whatever, gravel road. As you came, when you look at the little hills around here, those are well-drained mollisols, which are called U-dolls, those thick black A horizons. We have a lot of mollisols around here. The poorly drained ones, as you look in the broader flats or down the swales, are aquas, more poorly drained. That's because down here, the natural water table, actually the natural depth of saturation down the Okoboji was a foot above the soil surface. These were covered with water most of the years. And up here in where the clearing is now is 4 feet deep. And so we have these different soils that reflect a little bit difference in geology across here, certainly differences in water table depth, and differences in vegetation, because what grows with the water table is, you know, 4 or 5 feet down versus what surface is the difference between sedges and cattails and big blue stem. So we start seeing very different soil properties going across any given landscape. And that's where the relief factor comes in. What we have here versus here versus here, those are different soils. In the case of the harps right here, the pH of the harps, by the way, the surface here is 8.5. The Okoboji can be as low as 6. Because there's these little differences in going on that start driving big differences over the long term in what the soil properties are. But they vary by the landscape, and that's what the relief factor means. And that's what, when you look in a web soil survey for your particular field, will start telling you about the different soils you have across the landscape and what their natural properties are. And they reflect little tiny changes across the landscape. And so a better way to say it is this would be a relief where if I dug a pit up here, I might get a beautiful soil that looks like this. This one's been pretty seriously eroded. By the way, did I mention that Iowa, one of our long-term problems has been we have a lot of erosion. So here I have this. And when I come down here, I can start having this beautiful thick black A horizon all the way to a meter depth. So up here on top of the hill, especially if it's been eroded, this would be the bottom of the hill. And this might be 150 feet across. So the properties vary across at the landscape scale too. And as I've already said, maps available for this the maps are available. Just use Web Soil Survey or the Google Earth type stuff I was talking about. So what I'd like to end with in the next few minutes is just give you a little bit about what I think is going to go on for the 21st century, because we're well into it now, and we're going to spend the rest of our lives in it, I think. So what I want to see is, one is we're going to farm more intensely. And I say that to a PFI audience. I would say that to an audience. A couple months ago when I was speaking to some audiences for some of the seed companies and such, we're going to farm more intensely. Because our goal across the state, our governor wakes up wondering every day, is the yield going to be higher or lower in whatever we're growing next year. We're going to get smarter. We're going to do things a lot more sophisticated. And that's what you all are going to do, really, especially well. You're going to do it really, really sophisticated. But we're going to get more intense. Yes?
So wait, what do you mean by more intensity? How can we farm more intensely than Iowa?
Yeah, no. So Dr. Smith, you're setting me up for a really bad thing to say. No. How can we farm more intense given we do it? As an aside, by the way, I'll tell you right now, this is what I tell in my agronomy classes. We really, man, I don't really want to be shot today, but anyway, we really farm at a low intensity right now. You all don't. Many of you are farming much more intense. But, you know, I'm from a corn soybean farm. We had a diversified farm when I was growing up. You know, I grew up in the 60s and such, so, and then it got more and more corn soybeans. But, you know, I know places where fields were pragmatically maybe 120 days a year, there's actually something being used for that field's being used for. That's not intense. That's a third of the year the soil is actually being used. That's a definition of low intensity. So we're going to get a lot more sophisticated in what we do is what I'm saying. And there'll be a number of things we'll change. Far more than what I did here. Stefan was smart. He didn't ask me to talk about the future. I talk about the future, how I see it in the next 15 years, some other groups, and man, I see huge changes. I see the change between a landline phone, for those of us doing agriculture, versus the smartphone in the next 15 years. So that's how I see it. But, sir.
So I'm trying to get a handle on this. So conventional farmer more intensely means feeding the plant more often with chemicals that might help
Yeah,
improve yields versus an organic farmer,
right.
more cover crops, building the soil,
Yeah.
being able to farm more intensely.
And I see both groups. So the question is, am I saying for a conventional farmer growing corn, they might simply add fertilizers more often? For an organic farmer, it might be more with cover crops and such. I see these things all merging and just getting more intense. We're going to be growing things 300 days a year in Iowa intentionally. It's not all going to be harvested, but we're going to put a lot more biology into our system because we need to capture more photosynthate. We need to keep things around. And everyone's going to do it. We're also, so this is beyond this, but I say for the conventional farmers, pretty soon John Deere, whatever brand you like, is going to quit selling bigger and bigger planters, and it's going to sell 24 single row planters that are driven by a computer. Because that means I can now plant exactly what genetics I want, exactly where I want, every moment when I want it. I'm not bound by average soil conditions. It drives me crazy, coming back to this relief type stuff, it drives me absolutely crazy that people want to manage that whole field the same. The ecosystem was the same.
22, if you're going to farm more intensely and your carbon reserves are going to disappear quicker, then how are you going to increase yields when you're
Right.
from excess tillage?
So the question is, you know, as we do this more intensely, we will cause, a statement was, we will cause our carbon units of organic matter, which is really useful in soils beyond what I talked about here, but really useful, they're going to go down. And I see the opposite. We're going to put more plants, roots growing there more of the year. We'll build up organic matter across the board because we're going to do it a lot smarter. But it's beyond what I can talk about here. I'd be happy to talk about this some other time, but probably not right now. Is that okay, Dr. Galens? Excellent. But yeah, fun stuff. And I'm happy to have people tell me where I'm wrong in a million different ways. I'm really comfortable with that. I'm the 6 out of 7 children. I had older siblings telling me I was wrong for the first 40 years of my life. So, you know, I'm pretty comfortable hearing it. Yes, go ahead.
Part of the growth over time and intensity has been with fossil fuel energy.
Sure.
And you talked about biology. You think we can find something other than fossil fuels to increase the intensity?
Yeah, I think I think fuels will still be available, whether they're fossil fuels where we do more bioenergy, and that's something we'll probably see. We're going to see these things change. Yeah, I'm a tremendous optimist, and I say it that way. My smartphone's in the thing there, but you know I work with agriculture obviously a lot, and I always point out that when I talk to my students or here as a group, if I were to ask you what's going to change in your smartphone in the next 10 years, you're going to tell me the sky's the limit. And as soon as I ask you about what we can do with the 21st century knowledge we have today, people always tell me, yeah, we won't do that. And I see it'll be, no, the knowledge is there. We're going to change how we do microbiology of the soils, which will change lots of things. We're going to change how big equipment is for any farmer. And by the way, that'll be neutral. So I see farmers in Uganda that I work with, and I'll go see them in a month. I'm doing a project over there in a month. They'll switch to these microplanters too, and we'll see changes everywhere. What's available now, though, so rather than tell me how we did it, tell me what's possible. But that's, again, beyond it. Here I just want to talk about Iowa. But we're going to farm more intensely, and regardless of what that means and how we think about it, I will ask, how many people here don't think we'll farm more intensely in 10 years? That's who we are. It doesn't matter what my farming system is, I need the system to become more efficient. We're going to farm more intensely. And as a result, what I really want to point out in my discussion of soils, what that means is you and I will get a lot smarter in figuring out how to deal with water. You know, right now we're not particularly good always at dealing with infiltration. We're not really good at drainage, even though we have 1 million miles of storage of tile lines. And we're especially not good at really understanding water storage. Many of us count on the soil just naturally storing water. That's because we're really lucky that we have these nice parent materials like till and loess. We're going to become better at actually managing that. We're going to get a lot better at managing nutrients. We see leakage going on right now. We're going to see that leakage stop. We have to. And certainly regulations might drive part of that. But I see it as, right now, it's an inefficiency for farming systems. So ultimately, to get roots to grow, the way I always think about soils, the way I try to get people to think about soils as opposed to A horizon, B horizon, even though that's what the work I do, from a research point of view, what I really want us to realize is, let's think about what matters in the soil in terms of water behavior, nutrient behavior, how good is gas exchange, can oxygen get in? Because roots are controlled by how much oxygen is in the water at depth, not how much water is in the soil. Just like fish are controlled by how much oxygen is in the water, not by how much water is there. We've all seen fish die when there's low oxygen. Roots are the same way, the roots you and I want to grow. So it gets into oxygen in the soil, CO2 out, and then anchor support, waste disposal, nursery, symbiosis, all sorts of things. And the symbiosis part is basically the next speakers will talk about. I'm really excited about it. I can't stay for their presentations, but I'm really excited to see that because that's going to be the future. By the way, so that's getting microorganisms to work with the roots better, but I won't bore you on those things right now. By the way, the real thing that we're going to take into account beyond that is soil change. I want to point out that the typical, this is Doolittle Prairie. This is a slide from the top 10 centimeters, so top 4 inches of Doolittle Prairie, Little Prairie, about 10 miles north of here, just south of Story City. And by the way, I've done these same studies in a bunch of other prairies around Iowa, Kayla, Kelso, Denison, a bunch of prairies around Hayden Prairie, a bunch of prairies. This is what it looks like. If we grow corn and soybeans there after 50 years or more, this is what it looks like. Can you see? The black is solids, the white is pores. If I want to store available water, do I need a lot of porosity? If I want roots to really be happy, if I want oxygen to move through there, do I need lots of pores? This is the difference. So we're also going to start taking into account the fact that the soil changes as you and I use it. This natural monosol we have, these natural alpha soils we have, they're not always the same anymore. Just like I am the same guy I was when I started college here in 1977, but oddly enough, if you look at the photo, you would say I'm a different guy. Things change, and you and I are using the soil such that we change them. I will argue that most, if not all, my experiences with PFI members are, you're really, in many cases, taking the soil back more and more like this, which I really commend you for. That's why, part of why I'm so excited to be speaking with you all. But we have to take into account, and just so you know, I've had a couple of graduate students, a few graduate students do projects. They do all the work, I don't. Looking down to 1.5 meters, so 5-6 feet in Iowa, and we have changed soil properties in our cropping systems all the way to 5 feet in the soils we look at. Things change. Thank you, Stefan. So with that, the biggest payoff from all these improvements, really I'm going to talk about, or not talk about, but I'm alluding to, but you'll hear more about this afternoon and everything else you're doing. Our biggest payoffs will come that we'll get better soil quality, better soil health, so we'll have better and better soils, and as a result, we'll get better yields. So I'm pretty excited about the future, but as you could see even a few minutes ago, I'm excited because I see us making some big changes. Not in trying to have intense production, but realizing we can use equipment different than we have. We can do management systems very different and more sophisticated. But that's going to take a lot of learning. So we're going to use a lot more knowledge in our disciplines, which is exciting. And with that, what did I try to say for the last hour and 20 minutes? And I literally thought I had about a 40-minute, 30-minute presentation. Is the pedology of Iowa. If you want to know about the soils across Iowa, it's straightforward but important. We start thinking about a few things. We think about these different major landform regions with the two main parent materials being loess and glacial sediments. Prairie-derived mollisols, those thick black ahorizons, are very, very common across Iowa, but certainly in eastern Iowa there's a lot of forest-derived alpha soils, and really across the whole state there's local variability that matters. And that local variability is identified in these 500 soil series in Iowa. So what I'm really saying there is when you start talking to each other, it's good to do, and management makes sense. But if you really want to make sure you have the same soils, I might start looking at what series one person has or another and see how comparable they are. Because it's easy to think you and your neighbor have the same soils. They often aren't. I take students at Iowa State to the Rhodes farm, near Rhodes, Iowa, about 30 miles southeast of here. We're on a beautiful Loess-derived set of soils. We walk up a little tiny hill, just go a few feet, and we're in a beautiful glacial set of soils. It's easy to think that those soils are all the same. They change at all scales. And so finally what I'd say is Iowa is a beautiful place. So we should all be thrilled to be living here. We have a fascinating history, both natural and human. And last, it's a good thing you all have this workshop, good thing you're doing what you're doing, because soil-root relationships are going to get a lot more important in the future, will become a lot more sophisticated. So to some audiences, I would always ask them, how many of them take a shovel out in the field when they actually start thinking about the soil management? I won't with PFI because you all do. But most audiences I work with, they don't actually look at their soil. They look at the plant and they tell me what the soil must be. And they're wrong. So with that, thank you all very much. I really enjoyed it. And are there any more questions or comments, or did we have enough and you don't have any more questions? Sir. Right. Right. So this is from Doolittle Prairie, yeah. repeat the question? Yes, I'll try to do that. So the,
And what I was going to say at the end is, and then with the fall and spring tillage,
right.
like commonly been doing, what numbers would you see?
Excellent. So the question is, so what are the terms, the technical terms used to describe these things? So often what we'd say is there's been an increase in bulk density, so the amount mass per unit volume of Earth, so weight per unit volume, from 1.2 grams per cubic centimeter here up to about 1.5 grams per cubic centimeter. We'd also call that compaction, which is the same thing. Compaction and increase in bulk density really are referring to the same thing, with compaction implying there's enough material packed in the volume to start being a problem. And then the follow-up part of the question was, how about different styles of tillage, fall versus spring? What does it do? And that's a great question. So traditional tillage, and all tillage is basically designed to fluff up a pillow. It's to take something compacted and fluff it up so that you have more porosity again. That's one of the main goals. Then there's some other ones too, like warming the temperature and getting better seed-soil contact. But one component of tillage we try, whether fall or spring, is to fluff it up. In both cases, much of the fluffing up lasts maybe 60 days or so. So it lasts for a while. And then freeze-thaw helps with that too. But I want to point out, has anyone here ever tried to put a bunch of, I don't know, grain in a container? And if you want to get more in, what do? Shake it. So while in the short term it fluffs it up, in the long term that just helps reconsolidate it. And so I look at I'm a pedologist. I don't look at what happens in a given year very often. What I tend to look for is long-term trends. 20 years, 50 years, 100 years, 500 years, 1,000 years, whatever. And so the long-term trend consistently in tillage systems, my experience has been go from here to here. We keep shifting it that way more and more. And certainly we can offset it by tillage and such, and I did a lot of plowing as a kid. I loved moldboard plowing. I had to walk beans less the next summer, so I was all for that. But I realized now I was really making a change too. Great question, sir.
As you move from the right hand
Sure.
to the left hand,
Yeah. Right to left, okay.
and
Okay.
as you
Right to
towards
left.
that and begin to achieve it, would you expect maybe to be growing more perennial crops than annual crops because of the leaf?
Yeah, so when I came back to Iowa 22 and a half years ago, and I did some studies like this right up front, I was expecting, when I really dealt with degraded soils, not only compacted, but also loss in organic matter and compacted. And I did some studies on really severely damaged systems down near Lake Rathbun. It was a part of a project. Anyway, Department of Energy project. But I was expecting to be able to get it to go from here to here, so to go from the compact one to the less compact one. We wouldn't be able to see it we did about a 10-year study. I didn't expect to see much. And Iowa soils are so forgiving. Yeah, if you put perennial roots in there, lots of roots, perennial, more growth over the year, we can switch this back in just a few years. It's amazing how resilient, how fast our soils get better. They're sort of like being a 25-year-old, eating badly for 3 years, and then 3 months later they're in great shape. Even in tillage systems, we were seeing improvements. As long as they put more perennial roots out there, had more roots more of the time. That's why I talk about we need to get a lot more growth out there. We were also building up organic matter all the time. So even in, perennial systems. Yes. Yeah. Right. Tile, yeah. Right. So the question is, sort of what's my perspective on tiling? And one of your colleagues here is studying tiling too, so if she wants to step in ever, she's welcome to. But anyway, there might be a couple colleagues studying tiling, I'm not sure. But anyway, so what's my perspective on it? One is, wet springs, wet summers are a curse for our deep-rooted plants we want in our soils, in part because of our natural geology. So we know that. But after saying that, certainly what we're seeing now is as we add more and more tiles, people will say, well, it's lowering the water table. Maybe it is. I'm not convinced. I think what really is going on anymore is the tile lines are now conduits of oxygen coming in. And that's what we're really seeing as a benefit, is there's more oxygen to its depth by getting closer and closer tiles. Because that's really what the root needs. The water isn't drowning the plants, it's the fact there isn't enough oxygen in the system, and you had a bunch of oxygen. And the Australians have shown this with tile lines really nicely, putting in some beautiful tile lines and actually pumping oxygen intensely in. Man, they're seeing great yield response. So then, implicit to your question seems to be, what's the off-site impact? And I certainly question the off-site impact, because we are changing the residence time of the amount of water in the soil. When we combine it with the less porosity that we have, we really run the risk of increasing our drought, because with less porosity we can't store as much. With the tile lines, it's helping to remove it, so now we're doubling up that we have less water there. And as we try to get higher yield, we need more water no matter what. We need that water to pick the nutrients up and carry it in the roots. We need to have oxygen in it. So I really think there's a bunch of even in-field impacts. And I won't address what that means for Des Moines or something like that. I have enough people mad at me. I don't need to have even more people mad at me. Alice, yep, great, great. Okay, sounds good. Right. 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 Yeah, phenomenal question. One is, so Alice did a wonderful summary of everything I said, and better than I did, saying, we're really lucky with the right geology. We've had really nice biota. We have including plants and the microorganisms, and that overall plants will grow quite successfully here. And for the most part do, as long as you're a reasonably responsible steward, they can go great. And then Alice's question is that true, or is there more things we should be thinking about doing and such? One is, I would say yes. I mean, we have wonderfully, if we actually manage to close the loop, we have nice nutrient cycling and such, so we use a crop rotation and such, yeah, we keep seeing better and better growth. But ultimately, if we want that intense yield increase that I talk about, sometimes these economic yield, that's where we really start talking about other additions. And then coming back to the earlier question, if we want to minimize off-site impacts, like because we often tile drain our soils around here, then we need to be thinking of another scale there too. So the short answer is yes, you're right. If we want to maintain the status quo and just have the yields we have right now, the soils we'll have will let us do that for a long time. If in fact we want to ramp it up even more, then we need to keep ramping up our management, which means we're going to ramp up what we add, when we add it, how we add it more too, is the way I would say it.